Okay, welcome back. We are discussing this finite horizon problem. Let me summarize what we have. So we have the finite horizon intertemporal utility function plus the bequest motive. Okay. The constraint is this. So there is this other source of income, which is exogenous and fixed. Here, rho is positive, obviously. We have the initial level given. Then we looked at the present value Hamiltonian. So we have this times that. Okay. Then the first of the conditions will tell me u prime ct e to the minus rho t equals pt, obviously. Then I have the constraint itself. Then the co-state equation is p dot t minus that. So it is equal to, as you see, minus rpt. Okay. Now for the transversality, here we have something different, right? Because we are directly choosing how much to give our kids. So we have the marginal utility from bequest in present value terms, and this must be equal to the marginal cost. What is the marginal cost? Well, as long as the asset stock transforms itself into utility, then I decrease the value of it. Okay, that was the interpretation. So according to this interpretation, the marginal cost of not consuming it must be equal to that. All right? So we have these equations. Now be careful. If P dot T is equal to minus R PT, I have basically this solution. Right? So I know exactly how, sorry, yes, R. So I know exactly how it behaves, right? Now, obviously, we also have this. So if that's true, look at what's happened. So C prime AT is times minus rho T. Again, I have a typo here. So it will be minus rho T. Okay, so this will be equal to PT. So PT is at that date P0 e to the minus RT, right? Because of this. So psi prime AT will be equal to P0 e to the minus R minus rho T. Okay. Now this, my friends, will be QT, right? Because this is now the current value. So this must be the current value of it. How do I know that? Well, remember, we have this. If this is the present value, this will be the current value, right? I apply the formula conversely. So if I write Q dot T by the product rule, what do I have? The derivative of the first term times the second plus the derivative of the second term times the first. Okay, so if you do this math, what do you have? So you have at the end, let me just open a new page. So I have PT times e to the rho t equals qt, right? By definition. This is the definition. So from this, I have q dot t equals the derivative of the first term times the second plus the derivative of the second term times the first, right? So what is P dot T? P dot T is equal to minus R times PT. Rho T, PT. Then what do I see here? I see P to the P time, PT times E to the rho T times minus R plus rho. This is Q dot T. Now careful, this itself is defined as Qt. So Q dot T divided by Qt is equal to rho minus R. So Qt is equal to Q0 e to the rho minus R T, right? So in other words, Qt, now you can evaluate it in this way, rho minus R T, right? So it all boils down to the same thing, same co-state equation. This is the co-state equation that you would get if this would be an infinite horizon problem. All right. Now, to be more specific, of course, we're going to write the utility function in a particular way. Let's suppose that it is logarithmic. All right. Now, what do you know? You have u prime ct. Remember, e to the minus rho t equals pt, right? Or u prime ct equals qt, right? Because if you put that over there, it's basically qt. Then you have 1 over ct equals qt, under, of course, the assumption that ct is positive. Then ct is that. So you know exactly how much to consume, right? It's basically q0 to the power of 1, right? And e to the minus rho minus r t. In other words, you have the growth formula. So if this is C0, of course, it is C0 by definition. So you have the time path of consumption, which says this must be true in general, right? Now, obviously, once again, we have the saddle path type of situation, all right? So here, remember the state equation. And then you have now consumption basically satisfying this, e to the r minus rho t. Okay? So if you want to draw it, let's say you have AT here and CT here, right? Now, A dot T equals 0 is this, RAT minus CT plus gamma. In other words, equals 0. In other words, CT, RAT plus gamma. So it's a positive function of, so this is A dot T equals 0, right? And in this model, you notice one thing. First of all, you can basically tell me from this equation that A dot T, derivative of this with respect to CT, it is negative, right? So in this direction, when CT is increasing, this must be decreasing, right? So you have an increase here and a decrease here for AT, okay? But for consumption, you have what? As long as R is greater than rho, there's always growth, okay? So consumption will be growing in both parts. So if you suppose that there is a initial level, okay, let's say this is your A0, okay, you're going to choose a particular value of C0, okay, that C0 will be associated with a particular value of Q0, all right, and that Q0 will be a particular solution of this, okay. Now, how do we choose that particular solution? Well, I know where should QT go, right? Because that is now depending on my asset stock. Okay, if I do not choose it well, I cannot satisfy this. All right, so there is a particular point that would give me some growth path of consumption and asset stock. All right, now how do we know which one is true? I mean, which particular value is true? Well, you saw this proof in the handout for the Ramsey problem, right? Here we should be a little bit more careful for the balance growth, right? Because here, as you see, both AT will grow and consumption will grow, and that growth rate again should be a particular rate that would imply this in the long run, at the end of the horizon, right? Because there is this particular value, let's say AT, and this AT must be consistent with both this and this, okay, the growth. So, and that growth rate, I mean, where to start this growth depends on where to choose your initial consumption, how to choose your initial consumption. All right, so we are looking for then something like this. So growth rate of consumption is now fixed, right? It is R minus rho. And I have the growth rate of wealth stock. Now be careful. This is R plus gamma minus CT divided by AT. Okay? Now what does it tell you? If this is fixed, okay, and if you want a balanced growth situation, as I just draw, then this part should also be fixed. Okay, in other words, this number should converge to some constant. Okay, should converge to some constant. Again, here you can assume both ways. If it is positive, when AT is growing, in the very long run, it will go to zero. But anyhow, so here you see a type of balanced growth situation. How do you find Z star then? You will have something like this. You can tell me that R minus rho will be equal to R, or let me just revise it. So this thing must converge to that. Okay? In other words, gamma minus CT, AT should converge minus rho, or if you take, or you can tell me that CT minus gamma divided by AT should converge to rho. Okay? With gamma, for instance, if gamma is 0, it of course, it is simplified so that CT divided by AT is equal to rho in the long run, but be careful, I'm going to make this choice from the very beginning, right? So I express my consumption. Of course, this is only because we assume that utility is logarithmic. If it is not logarithmic, it does not simplify in this way. But if this is true, then I know exactly where to choose my initial consumption. Okay, and that initial consumption is that. So the slope of this figure is rho. Okay, if there's this theta angle here, it is equal to rho, and the slope of this, of course, is equal to r, right? The slope of this is equal to r, as you know it, because it is equal to so this is basically CT equals RAT, and the slope of this is now the balanced growth path, is equal to rho. So that growth requires this. Okay? That's the idea. So if the growth rates are equal, in the case of gamma equal 0, for instance, growth rates are equal, and that growth rate is equal to r minus rho. Okay, this is the growth rate. Then, since this is true for all t, including 0, okay, you can tell me that AT is equal to A0 e to the r minus rho t, then AT is equal to A0 e to the r minus rho t, capital T. Okay? That's it. So now I can answer your questions.
Summarize the whole optimal control theory.
I didn't get your question. Could you? I couldn't hear you.
Okay, can you summarize the whole optimal control theory things? If you can view of economic.
So you want me to summarize optimal control theory?
Yeah.
In non-mathematical terms.
Yeah. Yeah.
Okay. I did this before, but let me just do it again. So the idea is this: very simple idea, actually, not complicated. I'm in a situation. I'm a decision maker, and I have an objective function. My problem is that my objective function is defined for many different periods, not just in a static universe without time. Now my reward or objective is defined for many different time periods. In a continuous time universe, of course, these are all instants. Okay, so I have instantaneous profits, instantaneous utility functions, instantaneous loss functions, so on and so forth. Okay. In the simplest possible case, there is a variable which we call a state variable that will summarize the situation I am in, okay, at each instant. So there could be a resource, there could be a particular characteristic of myself as the decision maker. All right. It could be age, for instance, or it could be the skill of the stock of skills. It could be my income. It could be the asset stock I have. It could be any other thing, right? As long as it summarizes my situation, and as long so when I say this, of course, what I mean is this: I cannot change it in that instant. Okay, I open my eyes and I am in a situation. So that is my state. Okay. Now there are two different types of state variables. Some state variables are exogenous. Remember price and wage in the R&D problem. Okay. But some state variables are endogenous, which means in time that will change partially because I take some decisions. In the fishery problem, the entire stock of fish in my farm will change depending on the birth and death rates of these fish, but also depending on my extraction, how much fish I extract. Okay, so the simple idea is that if I take a decision today, looking at my state, looking at my situation, that would affect my reward, not just for today, but in the future as well. Because my decision today, given my state today, will explain my situation, my state tomorrow. All right? Obviously, then, there is a dynamic trade-off between today's rewards and tomorrow's rewards. Today's objectives and tomorrow's objectives. Okay? In the optimal control theory, we want to solve such problems, of course, optimally. Okay? That's it. And for this, of course, we are not looking at, in a typical static optimization problem, what we are after are basically values, right? Given your income, how much to consume from the first good, how much to consume your second good, if incomes and prices are given. Now here the situation is a bit different. What we are looking for is a path. Is the evolution of my control variable and the evolution of my state variable, and I take all these decisions today, starting in the present. So I create this optimal plan. All right. When I stick to the plan, if there is a solution, of course, and by solution again I mean the dynamic path, dynamic optimal path, then that path will take me to a sort of a steady state. And along the path, I will be maximizing my rewards, not simply the rewards at each instant. That's not the case, because I am giving different utility weights to different instances given the discount rate. Okay, so that would be a verbal, non-mathematical explanation.
Okay, thank you.
All right. Now, there's one last thing. In a problem like this, of course, you can also tell me that what happens if there's no bequest motive, right? What happens if there's no bequest motive? Now, I want you to first imagine this. So this would be the transversality condition in the case where horizon is infinite, right? when horizon is infinite, that would be the transversality condition. Okay? Then you may tell me simply this. Right? Now, what's happening here? Remember, I told you that so this is like a control variable, right? For the problem that we are studying, like a control variable, right? Because I'm choosing it. Now, this type of condition tells me that, you know, forget about the bequest motive for a moment. As in the static models, right? If it is valuable, consume all of it, right? If it is not valuable, you can leave some of it. All right. So in general, you have something like this, because basically here we take T to be finite. Okay. Here we basically take T goes to T. Okay. So if there's no bequest motive, everything, almost everything will be the same. All right. There's a problem with my pen here. Okay. It's because of the color. So here, from going from this to this, what we basically do is this, right? So in general, this will summarize your transversality condition. All right. But the earlier problem is a bit different. Why? Because the consumer has a bequest motive. Okay. So this does not apply. All right. But here, without bequest motive, what we require in general is already true, right? Because consumer is already described by the by this condition. Okay. So there's a nice derivation in the textbook. You can actually check it. In that derivation, you basically see how the total amount of resources. So it is called intertemporal budget constraint. So how the total amount of resources can be used to write a formula for asset stock. Okay. And your optimal plan, of course, now requires a different dynamic path, right? Because now, if this is AT and if this is A0, you're going to find a way all right, you're going to find a path that will make you converge to this point, which is 0. So at the end, it will be equal to 0. So if you choose there, you may go something like this. If you choose here, you may go somewhere like this. All right. But if you choose a particular initial consumption, okay, that asset stock will be equal to 0 at the final date. All right, because that's the constraint. So again, the transversality constraint, so that part is the same. The transversality constraint allows you to choose C0 and Q0 and P0, obviously. Okay? That part is the same. And that's all for optimal control theory. Now we have 4 minutes. I can respond to your questions. We can log in again if you have more to discuss, or if you have more serious problems than optimal control theory. And obviously, your midterm exam will cover all the topics that I taught in the last 7 or 8 weeks, right? I'm hearing you now.
I don't have any question or problem.
Okay. All right. So in the exam, Bilal, are you going to say something?
Sorry, is it possible to schedule a general overview of course before the midterm exam?
Okay. That would be if it will be socially welfare improving, I'm open to such ideas. But in such a review course, I expect you to ask me questions. All right. All right.
Yes.
You get the point.
Yeah.
So I will not give the same lecture I did in the last 7 weeks. You see my point? So if you study, work, solve some problems, all right, because in my website there are tons of problems. Then if you ask me questions, knowledgeable, smart questions, then I am open to that. If you are going to sit down there without doing almost nothing, all right, without asking questions, without generating comments, without doing almost nothing, then I will not hold a review session, because you up until so far you haven't deserved it. All right. So if you're going to work hard, solve some problems, if you're going to ask me smart, knowledgeable questions about nonlinear programming, about optimal control theory, about dynamical systems, then I can do it. I can do it for a whole day, as long as I see you are benefiting from it. But if you're going to hear me again and again and again and again, just open the video in the YouTube and just hear me again. Right? So you think about it as a classroom, all right? As a members of a class, you take a decision on this, and then we can do it over Thursday, I guess. My Thursdays are better for that. My Thursdays are open.
Okay, we can discuss on WhatsApp or somewhere else.
WhatsApp is a bit more difficult for me because
no. As a classroom.
Yeah. As a class, as a cohort, you take my advice. Now I think I'm clear in explaining my limits. All right, we have less than a minute. Obviously, you have no questions. So I'm now ending this session, and see you for the midterm. I mean, I will not see you, but you're going to take the midterm, and I will see you in 2 weeks. All right? Bye-bye.
Okay, see you.